Hey, hi everyone. Welcome to another Graphs and Matroids seminar. Today we have Youngho Yu from Georgia Tech, who's going to be talking about packing A-paths of length 0 modulo prime. Youngho.
Okay, thank you, Shayla. Thanks to the organizers for the opportunity to speak here. I'll be talking about packing A-paths of length 0 modulo prime, and this is all joint work with Robin Thomas. So first, let me define what A-paths are, and they're a nice way to generalize matching. So let's start with a very basic inequality that everybody you should know, and that is that if you take the maximum size of a matching, and then the minimum size of a vertex cover is at least the maximum size of a matching, because a vertex cover is a set of vertices that intersects every edge. So the first inequality is trivial. But the second inequality is also sort of trivial for matchings, and that is that the minimum size of a vertex cover is bounded above by 2 times the maximum size of a matching. And the way we get the second inequality is that you just take some maximal matching, and you take all the vertices that are in the matching. And that is a vertex cover for all the edges. So this is a very easy inequality. Okay, but it turns out that this inequality generalizes in a very nice way to A-paths. So let me define what A-paths are. So if you give me some set of vertices in my graph called A, then an A-path is a non-trivial path with both endpoints in A that is also internally disjoint from A. So here's a picture, and this is a generalization of matchings, because if A is the entire vertex set, then A-paths correspond exactly to the edges of the graph, because it is required to be non-trivial, has to have at least one edge, and it has to be internally disjoint from A. And Galai showed it in 1961 that this inequality generalizes to A-paths. So the minimum size of a set of vertices that intersect every A-path is at most 2 times the maximum size of a packing of A-paths, or just a set of disjoint A-paths. And this is not as easy to show as in the case of a matching. But what Galai actually did was he proved a generalization of the Tut-Berge formula for matchings. It turns out that the formula for the maximum size of matching generalizes to the maximum size of a set of disjoint A-paths. And this inequality is a consequence of this formula, this exact min-max formula. Okay, so that's a nice classical result of Galai for A-paths. There's another generalization of this called S-paths. This was done by Motter. So it's a special kind of A-paths. So if you give me a set of vertices A, and if you give me a partition of A called S, then an S-path is an A-path with the constraint that the 2 ends of the path has to have its endpoints in distinct parts of this partition. So this is again a generalization of A-paths, because if S, the partition, is just a set of all singletons, then every A-path is an S-path, because you can't possibly have 2 endpoints in the same part of the partition if all the parts are singletons. Okay, and Motter showed that this exact inequality, and actually the same generalization of Tut-Berge formula, it further generalizes to S-paths. So there is again a exact min-max formula, which gives, as a consequence, this nice inequality, that the minimum size of number of vertices you need to hit every S-path is at most 2 times the maximum size of a packing of S-paths. And there is yet a further generalization. But to describe that, I first need to explain what group label graphs are. So in this talk, we'll be talking about 2 different models of group label graphs. So a group label graph generally is just a graph with its edges labeled by some elements from a group. And there are 2 models, the undirected model and the directed model. And the only difference between the 2 models is that when we look at a path, when we calculate the weight of a path, In the undirected model, you just add up all the weights of the edges in the path. But in the directed model, you care about the orientation. So you start with some orientation of the underlying graph. You have weights on the edges, and if your path or if your walk traverses the edge forward, then you add the element. If your walk traverses the edge backwards, then you subtract the element. Okay, and note that the two models are equivalent if every element of your group has order 2, because in that case, every element is equal to its inverse. So adding and subtracting are the same thing. Okay, and here is the generalization of S paths to group label graphs. So the generalization turns out to be non-zero A paths. So if you give me a group label graph, a directed group label graph, and if you give me some set of vertices A, then now I'm looking for A paths that have a non-zero weight. Okay, and let me show you why this is a generalization of S paths. So let's take the same picture as before, but now I need to define a group labeling on it. So orient the edges arbitrarily. Here it doesn't matter, but now the group is going to be the integers mod 2. And we take many copies of the integers mod 2, and the number of copies we need is just the number of parts in the partition. So for each part, you pick some coordinate, and you put for every edge that is incident with that part, you put a 1 in that coordinate and 0 everywhere else. So here in this picture, we have 4 parts. So our group is z mod 2z to the power of 4, and we put these binary strings as weights, and everything else has weight 0. Okay, and it's easy to see that if we put back these A paths that we had before, an A path is an S path if and only if it has non-zero weight. Because if you go back to the same part where you started, then you'll be adding this binary vector by itself, which would give you 0. So it's non-zero if and only if you start and end in different parts. Okay, and this very nice theorem of Chodnovsky, Gillen, Gerard, Godin, and Lohmann, and Seymour from 2006 is that if you give me an arbitrary group, so it doesn't have to be abelian, it just doesn't even have to be finite, just arbitrary group, then in the directed model of group labelings, the same inequality holds, and in fact, this sort of the same exact min-max inequality, or sorry, exact min-max relation that generalizes Tut-Berge formula for matchings, that also generalizes to these group labeled non-zero A paths. So this is a very nice theorem, and has a very nice proof that uses matroids. Sorry, I mentioned that here. Okay, and there are actually even further generalizations of this exact min-max formula. So Pap, shortly after this result, he showed that for what he calls non-returning A paths is a slight generalization of these non-zero A paths in group label graphs. Okay, and more recently, Gillen and Rodriguez showed that if you take a biased graph, so a biased graph generalizes these directed group label graphs. If you start with a biased graph and you take some certain non-balanced A paths, they also satisfy this exact min-max inequality, and therefore also this this approximate packing coupling duality. Okay, so these are some very nice results for in the directed setting. Is the very nice sequence of generalizations. Okay, but for this talk, we'll mostly focus on the undirected version of group labeling. So can we also get this type of inequality for the undirected model? And it turns out the answer is yes, but the inequality is not as nice. We don't get 2 times the maximum size of packing. We get something looser, but we still get a bound. So Wolin showed in 2010 that in the undirected model of group label graphs, if you take any abelian group, then the minimum size of a hitting set or set of vertices that intersect every non-zero A path is bounded by some function of the maximum size of a packing. where this function it grows to the order of a quartic. Okay, and I don't believe it's known whether or not this is optimal, but for this talk, we only care about whether or not there exists a function that bounds these two quantities. Okay, so here I think is a good place to introduce this notion of the Airish-Posha property. So if you give me any family of graphs, so think of sort of cycles or A-paths or special kinds of A-paths, we say that this family satisfies the Airish-Posha property if there exists a function f such that in all graphs we have this inequality that the minimum size of a hitting set for all subgraphs in f is bounded by a function of this maximum size or packing of subgraphs in f. Okay, so the name comes from this classical result of Airish and Posha from the 60s, that the family of cycles satisfy this property. Okay, but for this talk, we'll mainly focus on A-paths. Okay, and one immediate corollary of this theorem of Wolin is that if you give me any positive integer, then the family of A-paths of length non-zero mod m, they satisfy the Airish-Posha property. Right, and I think the main differences between the undirected model and the directed model is that, well, so the one thing I know that the undirected model can do that the directed model cannot is modularity constraints, where the modulus is greater than 2. But there are other things that the directed model can do that the undirected model cannot. For example, if you can encode sort of the fundamental group of curves on surfaces, it is more naturally modeled in the directed model. But in the undirected model, we can handle these modularity constraints. Okay, so what more is not known about A-paths with more modularity constraints? So I just copied down the definition. So Brun, Heinlein, and Yost, they showed recently, or in 2018, that the Airish-Posha property also holds for even A-paths. You should note that for odd A-paths, this is a corollary of the result for non-zero A-paths as well in either model. But for even A-paths, they showed that this also holds. But it does not hold for A-paths of length 0 mod m, where m is any composite that's at least 6. So for 4, they don't say anything about 0 mod 4, but for any other composite number, they show that it does not hold. So here is the construction that shows that the Airish-Posha property fails. So if you look at integers mod 6, take a very large grid, and the vertices in A are the two columns of vertices in the left and the right side. So if we want, and all the unlabeled edges are 0. So if we want a path of length 0 mod 6, we have to start from the left side and end on the right side and use an edge in the top row. Because if you start and end on the left side, then your length will be some multiple of 3 plus 2. And if you start and end on the right side, then your length will be some multiple of 3 plus 4, which will never be 0 mod 6. Okay, and it's easy to see that if you look at the paths that go from left to right, but also use an edge in the top row, you can't find two disjoint paths of that form, just because of planarity of this grid. So the maximum size of a packing of A paths of length 0 mod 6 is 1. You can't find more than 1. Okay, but we can make this grid as large as we want so that the minimum size of a hitting set can be made arbitrarily large. So there does not exist a function that bounds the minimum size of a hitting set in terms of the maximum size of a packing. Okay, and this same example generalizes for all other composite numbers except 4. If you try this construction for 4, you'll find that it doesn't actually work. Okay, and it turns out that for 4, 0 mod 4, the Airish-Posha property actually does hold. So this was a result of Brun and Ulmer in 2018. Okay, and this is so the proof for even A paths is relatively simple, but this 0 mod 4 result is quite a bit more complicated, and it uses the structure theorems for group level graphs. Okay, but this was the state of the results, and the only remaining cases for 0 mod m is when the modulus is an odd prime. Because for every composite that's not 4, it's false. For 4, it is true. For even A path 0 mod 2, that's also true, but the only remaining cases were odd primes. And our main result is that for an odd prime, the A paths of length 0 mod p, they also satisfy the Airish property. So this covers all the remaining cases. But the proof, it really uses structure of group label, undirected group label graphs. So it's natural to also ask, when does the Airish property hold for 0 A paths in group label graphs? Okay, so we also characterize when the 0 A paths satisfy the Airish property. It turns out there's not much more. So for integers 0 mod prime, it is true as we from the main result. 0 mod 4 was a previous result. And the only other case where the Airish property holds is when you put copies of integers mod 2. Okay, so how do we get this last case, integers mod 2, many copies of integers mod 2? Well, so recall that when every element has order 2, the two models, the undirected and the directed models are equivalent. So to handle this case, what we do is we actually show that in the directed model of group label graphs, the Airish property holds for 0 A paths as long as the group is finite. So if and only, it's an if and only if. So as long as the group is finite, the Airish property does hold for 0 A paths in the directed model. Okay, and we can also further ask, okay, so we've characterized 0 A paths. What if we just require the A path to have some fixed length? Okay, and we also obtain a characterization of abelian groups gamma and elements L of gamma, such that A paths of weight L satisfy the Airish property. And again, it turns out you don't get much more than the 0 A paths. So let me quickly give you the outline of a proof of this last theorem, assuming that the Airish property holds for 0 mod p A paths for primes. Well, okay, let me first tell you why we need the finiteness condition. So if the group is infinite, then there's this simple counterexample. So we can always choose a sequence of elements, G1, G2, and so on, where when we choose a next element, we just avoid the previous elements and the inverses of the previous elements. Okay, and we just make a large grid. We put the elements in order on one side, and we put the inverses in the other order on the other side. So now a 0 A path has to go sort of diagonally across this grid. So you can't have two disjoint 0 A paths. But of course, we can make this grid large enough, or arbitrarily large, so that the minimum size of the hitting set will be arbitrarily large. Okay, and if you're familiar with the Escher wall construction for odd cycle, this is essentially the same thing. So if the group is infinite, there's no hope of possibly obtaining the Airish property. Okay, so now let's assume that the group is finite, and let's also assume that the length that we're looking for is non-zero. For a 0 case, we can reduce to the previous theorem. The construction for integer 0 mod 6, it actually generalizes to every group. That's not one of these three groups. Okay, so here we'll come up with some other construction. So suppose there exists some non-zero element, G, such that G does not generate our desired length L. Okay, and that's enough to construct another counterexample. So this here, essentially that's a very similar counterexample. But on one side, we put L minus G, on the other side, we put 0, and on the top row, we put G, and everything else also has weight 0. Okay, so again, I claim that every A path of length L has to go from left to right and also use an edge in the top row, right? Because if it goes across without using the top row, then your weight will be L minus G, which is not L. If it starts and ends on the right side, then your weight will be some element generated by G, which does not contain L. And if you start and end on the left side, your weight will be 2L plus a multiple of G, but that's not equal to L because L is not generated by G. But the only way for 2L plus a multiple of G to equal L is for L to be generated by G. So as soon as there is some non-zero element G such that L is not in the group generated by G, we get a counterexample. So we can assume that every non-zero element generates L. Okay, and this is a very strong condition. What we can deduce from this is that L has prime order. So why does it have prime order? If L does not have prime order, then if its order is composite, then you take, let's say the order of L is m times n for some integers m and n greater than 1, then you just take m times L. That's not going to generate L. So if L has order 6, take 2L. 2L is not going to generate L. So L has to have prime order. Okay, and gamma has to be a P group, which means every element, the order of every element in the group, it has to be a power of P. Because if there was some distinct prime that divides the order of the group, then you just choose some element of order that the other prime, and that's not going to generate L. So gamma turns out to be a P group. Okay, and we also get that L, the subgroup generated by L, is the unique subgroup of order P. Because if there was some other subgroup of order P, that has to be generated by some element of order P, and that's not going to contain L. Right, so we have a unique subgroup of order P in a P group, and it turns out it's a group theoretic fact that if these two conditions are met, then the group is either cyclic of prime power order or a generalized quaternion group. So this is a well-known group theory fact that shows up in many textbooks about finite groups. So because of this condition that every non-zero element has to generate L, we deduce that the group has to be cyclic of prime power order, because the generalized quaternion groups are non-abelian, and for undirected group label graphs, we only care about abelian groups. Okay, and if once we know that it's a cyclic prime power cyclic group, it's easy to finish the proof. So I won't go into the details, but just want to mention that this is how we use this group theoretic fact. Okay, so that is the characterization. But this raises a question of the directed model of group label graphs. So in the directed model, it's very easy to accommodate non-abelian groups. So the natural question is, can we also characterize the groups and the lengths or weights L such that A paths of weight L satisfy the Airish-Poiseuille property in directed group gamma label graphs? Okay, and it turns out that the same construction also works in the directed setting. So we can also apply this group theoretic fact, and we only have to look at the two cases of cyclic prime power groups and the generalized quaternion groups. So if you can sort of decide just for these two kinds of groups whether or not the Airish-Poiseuille property holds, then we would also have a characterization. Okay, and mainly I'm just interested in whether generalized quaternion groups have any kind of meaningful role in the Airish-Poiseuille property. I'm not sure if that's the case, but it will be but I don't know the answer. Okay, so for the rest of the talk, I'll prove this main theorem that the Airish Pochard property holds for A paths of length 0 mod P if P is an odd prime. So maybe I'll take a second here and ask if there are any questions. Okay, so let's move on to the proof of this main theorem. So the proof goes through some structure theory, especially coming from the graph miners project. So the main sort of tool that's used in this proof is tangles. So let me explain how these tangles come up with this Airish Pochard property. So let me just remind you what the definition of Airish Pochard property. So if you give me a family of graphs, then the family F satisfies the Airish Pochard property if there exists a function F such that for all graphs, this inequality is satisfied, where the minimum size of a heading set is at most F of the maximum size of a packet. So suppose this family does not satisfy the Airish Pochard property. That means for all functions F, there exists a graph G such that this inequality is violated. So let's take a minimal counter example. So we have the freedom to choose the function as large as we want. So let's choose some very fast growing function and suppose that the Airish Pochard property still doesn't hold with respect to this function. Okay, then there has to exist some graph G such that this inequality is violated, which means that we can find some graph G and some positive integer K such that G has no packing of graphs in F of size K. And G has no hitting set, no small hitting set for the graphs in F. Okay, and subject to these two conditions, we'll minimize K. Okay, so this is the definition of a minimal counter example. I fix some very fast growing function F, and I take some graph G and an integer K such that I don't have a large packing, and I don't have a small hitting set. Okay, and then minimize K. Okay, then what turns out to happen is that this defines a tangle. So what is a tangle? Well, let me first explain what. So if I take a small separation is just a small set of vertices that separate the graph into, well, it's a small separation is a union of two graphs whose intersection is the entire graph, and they meet in a small set of vertices. Okay, so I claim that whenever I take a small separation, exactly one side of the separation contains a graph in F. Okay, so here's the proof. So take a small separation A and B. Suppose that neither side contains a graph in F. Then that means if you take the vertices in the intersection, that's going to be a hitting set for all subgraphs in F. And that violates the second condition, because we're assuming that there isn't a small hitting set. Okay, so now suppose that both sides contain a subgraph in F. Well, so now, so if A minus B contains a subgraph in F and B minus A contains a subgraph in F, you can just forget one of those sides and just focus on one side. If I can find K minus 1 disjoint copies of graphs in F on one side, then I can put it together with the 1 from the other side to get a packing of size K, which means I don't have a packing of size K minus 1 on either side. Okay, but because we chose K to be minimal, this means that there has to be a small hitting set if you restrict to each side. And so you take these two small hitting sets for each side, and you take the union of those two small hitting sets with the intersection of A and B. And you will get some small hitting set for the entire graph. So whenever I get a small separation, there is only one side of the separation that I sort of have to care about. Okay, and this turns out to define a tangle. I won't fully define what a tangle is, but it's really just an orientation of the small separations, of all the small separations in the graph, such that they all sort of point to this one large highly connected part of the graph. Okay, and it turns out that we get this tangle where the highly connected part of the graph that we care about is where we will find all these A paths or whatever subgraphs we're looking for in there. So now if you restrict to A paths, it turns out we need a slight modification of this. So it turns out that it's a bit more convenient to find a tangle after you delete the vertices in A. And the proof of that is slightly more technical, so I didn't give a proof, but it's still the same idea. So now let's restrict to families of A paths. Okay, so if G and K is a minimal counterexample to these special A paths satisfying the Airish-Boccia property, then we can find a large tangle in G minus A. After deleting all the vertices in A, in the remaining graph, I can find a large tangle. Okay, and what the property that we get is that there is some highly connected component of the graph that is pointed to by this tangle, where every A path, every special A path that we care about is highly connected to this highly connected component. So there is no small separation that separates this special A path from this highly connected part. So I'm trying to avoid giving the full definition of tangle. So this, I know that it's very vague, but this is the best I could come up with. Okay, and the fundamental result, one of the fundamental steps of the graph miners project is this grid miner theorem. So Robertson and Seymour showed in 1986 that whenever you have a large tangle or a very large tangle, you can find some large wall in the highly connected part of the tangle. Okay, so a wall is just this grid-like graph, except it looks like a bunch of rows of bricks. Okay, and the reason we use walls is because a wall is subcubic, and subcubic graphs behave more nicely with respect to graph minor relations, because having a wall as a minor is equivalent to having the wall as a subdivision, which is not the case for actual grids, because they have vertices of degree 4. So I mean, when I first learned about walls, I thought this was like a very strange, unnatural object. But it turns out I was wrong. It took me actually more than a year of working with this problem to realize that this is actually just the hexagonal grid. So I mean, in some sense, a hexagonal grid is more natural than a square grid, at least to me. So a wall is just a hexagonal grid, but we define it this way because it's easier to define, I think. So the grid miner theorem says that if you have a very large tangle, then you have a very large wall or a hexagonal grid. Okay, and so what we do is we refine this grid miner theorem to undirected group labeled graphs. So what we show is this structure theorem for undirected group labeled graphs, that if you take a group labeled graph with a very large tangle, then I can find, well, we can find a very large wall. That's just from the grid miner theorem, but we can also sort of refine the structure of this wall in terms of the lengths of the edges. So there, I can, for example, I can find a very large wall where every brick is a non-zero cycle. Or I can find a large wall where every brick is a zero cycle, but I have these nice non-zero linkages on the outside of the wall. Or one of these kinds of configurations. So I won't describe all these in detail because it gets a bit technical. But at a high level, what we obtain is that if I have a large tangle, then I either get many non-zero cycles that are distributed in one of few sort of predictable configurations or controllable configurations that are all highly connected to the tangle, or I can find a small hitting set for all the non-zero cycles that are highly connected to the tangle. So either I get many non-zero cycles, in which case I can sort of control what they look like, or I can destroy all the non-zero cycles with a small hitting set. So what do we do when we get a lot of non-zero cycles? So here is just a simple structure that allows us to find an A path of length 0. So the two black endpoints, those two vertices are in A. So I take an A path, but with these sort of paths attached to the main path in a sequence. So I call this a cycle chain because it's sort of a chain of cycles. Okay, and the two endpoints, the two black vertices are in A, and none of the internal vertices are in A. And I call it a non-zero cycle chain if for each of the cycles that are on this path, the two paths I can take to go from one side to the other, they give me different weights. All I care about is that they give me different weights. So if I get a long enough non-zero cycle chain, then I can sort of reroute the path along some subset of these red paths. And the hope is that I can find the special path that I'm looking for. And it turns out that if the group is the cyclic group of prime order, then this is always possible. So any long enough non-zero cycle chain gives me a 0 A path. And this is just from the fact that every element is a generator for the entire group. Okay, and this is really where the Airish push-up, we can see that the Airish push-up property fails for when the group is when the modulus is composite, because for integers mod 6, you could have an arbitrarily long cycle chain, and you could not have it's possible to not have a 0 A path. For example, like the entire black path could have length 1, and whenever you reroute one of the PIs to the QIs, you could gain like 3. So no matter how you reroute your path in the cycle chain, you'll get 1 plus a multiple of 3, which is really just like the counterexample that shows the construction. Okay, but for primes, this always works. Okay, so all I need to do is I need to go to my structure theorem and find many of these non-zero cycle chains. Okay, and it takes some technical work, but the idea is very simple. It's just routine technical work. So one possible configuration that I get is that I get a large wall where every brick is a non-zero cycle. Okay, then I just find many different paths from A to the wall that link in this nice way. I can find, if the wall is large enough, I can find these long enough paths with as many these non-zero cycles attached as I want. Okay, and the other cases are very similar. So what happens if we don't get many non-zero cycles? So there's a small hitting set for the non-zero cycles that are highly connected to the tangle. Okay, so let Z be some small hitting set. Okay, so what the structure that we get is that after we delete Z, there is no non-zero cycle that's highly connected to the tangle. Okay, and this is what we define as gamma bipartite. It just means there are no non-zero cycles. Okay, but we don't get that in the entire graph. We just get that the part that's highly connected to the tangle doesn't have a non-zero cycle. So the right structure to look at is the 3 block that is that belongs in the large part of every small separation according to this tangle. And this is really where most of the headache comes from with this proof, because when we look at the 3 block, So the main difference between the directed model of group labeling and the undirected model is that in the directed model, if you know that you have no non-zero cycles, then you can always do these shifting operations to make all the edges to be equal to 0. You don't need any connectivity assumptions. But in the undirected model, you actually need 3 connectivity to conclude the same thing. So what we want is to get this large graph in this highly connected part of the tangle where all the edges have weight 0. Because those are simpler to look at or to work with. But it turns out we need 3 connectivity to get that. So we need to work with the 3 block that's in this large part of the tangle after deleting this small hitting set. Okay, so yeah, 3 connectivity suffices to conclude that every edge actually has weight 0. Okay, so what do we do with this 3 block? So we have this set A, and below we have G minus A, and we also take away Z, which is a small hitting set. We don't care about Z anymore. And in the remaining graph, I have this 3 block. So think of this black part of the picture. That's some 3 block of the remaining graph that's highly connected into the tangle. And every edge of the 3 block has weight 0. So if I can find paths from A of, let's say, some weight L to one of these vertices and minus L to some other vertex, then I could just link these up in the 3 connected part to get an A path of weight 0. But the problem is that the 3 block is not actually a subgraph of my graph. The 3 block is actually, it's some set of vertices where we have these bridges that attach to at most 2 vertices of this 3 block. And the vertices in A do not have to attach directly to these vertices of the 3 block. They can attach to one of these bridges and then go to one of these vertices in the 3 block. And this causes a lot of problems. It's very difficult to link this red and green path, because before I could just say, oh, okay, the red path goes to this vertex in the 3 block, the green path goes to this vertex in the 3 block. We can just take the set of these edges that of length L and minus L to the 3 blocks and then just link them together. But we can't actually do that because of these attachments or these bridges. Okay, and I tried for quite a long time to see if I can just handle this with using some sort of a gadget where I replace each bridge with some gadget, but it doesn't seem to work. Yeah. So this part, we actually have to do quite a bit more work. So what I end up doing is, okay, I'm going to look at all the vertices in A that attach to one of these blocks, one of these vertices in the 3 block with a path of length L. And I look at all these vertices of A that attach to a 3 block with a path of length minus L. And I want to apply some sort of a Menger type theorem where I find a path from the L path vertices to the minus L vertices. That'll give me a 0 A path. But I can't really do that directly. It's hard. I couldn't figure out a way to do that directly. So what I did was I find some large wall inside the 3 block. I find many disjoint paths of weight L from A to this wall, and separately, I find many disjoint paths of weight minus L from A to the wall. Okay, and still this is not easy because we still have to deal with these the ways that the vertices in A can attach to these bridges. It gets quite technical. Okay, but so now the question is, okay, now I need to find paths of weight L, like I need to specify the length, paths of weight L from A to the wall. So this is essentially a Menger type of problem, right? I'm looking for paths from one set of vertices to another set of vertices. But I'm requiring that these paths all have weight L. So this is now the problem that we have to solve, is this approximate Menger type problem. And approximate Menger type, I just mean Airish Pochette property for AB paths or certain special AB paths. So can we find many disjoint paths, AB paths of length L or a small hitting set? In other words, does the Airish Pochette property hold for AB paths of length L? Okay, and it turns out the answer is no in general. The same the construction that we had before for, like, say, the integers mod 6, the same counterexample works when we take one side to be A and the other side to be B. very similar kind of construction works for in this case. But actually, it turns out that you can do this. So this holds if one of the vertex sets, so if B is contained in some bipartite 3 block, then this is enough to make this approximate vector type result hold. Okay, so we apply this result. So we find many paths from A to the wall with weight L, and then separately we find many paths from A to the wall of length minus L. Okay, but now these paths could all like sort of intersect each other in undesirable ways. And also, I'm ignoring the fact that when we find these paths to the wall, like the paths themselves could intersect the interior of the wall. So we also have to do this cleanup so that the paths don't intersect, they only intersect the boundary of the wall. Okay, so now what do we, so once we obtain these two linkages or these two sets of paths, we can finish off the proof with this, this Ramsey type argument. So let's suppose that I find many red paths and many green paths. If I can find k red paths and k green paths that are all disjoint from each other, then will they all link to this wall? So I can link up the ends of the red and green paths inside the wall. Okay, and it's easy to see that if you take any sort of k vertices and any two sets of k vertices on the boundary of the wall, you can always link them up inside the wall. Okay, so suppose that there does not exist sets of k paths on each side where they're all distant from each other. And we can apply this bipartite Ramsey theorem to obtain a set of k red paths and k green paths so that every red path intersects every green path. So this is just applying the bipartite Ramsey theorem that every bipartite graph either contains a complete bipartite graph on k vertices on either side or an empty bipartite graph on either side. So once we get that, once we get these k paths on either side that all intersect each other, we can now just look at the union of these paths and we just apply Youngho's theorem. So that's essentially the outline of the proof. So let me just summarize. So we characterize the abelian groups gamma and the elements L of gamma such that the Airish Poisson properly holds for a path of weight L in undirected group label graphs. And I already posed a problem of getting the analog of this result for directed group label graphs. And we only have to look at cyclic prime power groups and generalized quaternion groups. Okay, and also in the undirected setting, it turns out that the inverses of elements don't really play a big role when we look at undirected group label graphs. So in the directed group label graph setting, the fact that you have inverses of these elements is crucial, because whenever you traverse an edge, depending on the direction you traverse the edge, you have to add the element or its inverse. Okay, but in the undirected setting, we're only adding stuff. We're only applying this binary operation, and we're never really taking inverses. So I mean, one question is, can we generalize any of these structure theorems or any of these results to non-abelian groups? But I think it's very natural to ask, do we even need inverses? So I think it's an interesting question to see how much of this generalizes to monoids. So monoids are just a set equipped with an associative binary operation and also an identity element. So it's a group, except you're not allowed to have inverses, or you don't always have inverses. So I think a lot of these things in the undirected group label graph setting could generalize to monoids. Okay, and another way to generalize these results is to look at subsets of the group and say I'm only interested in A paths whose weights are in this subgroup. So one of the first results of Wolin was that if you give me any group, the non-zero weights, they satisfy the Airish Borchardt property. So in that case, this subset L is all the non-zero elements. Okay, and we show that if L has size 1, if L is just one single element, then we know exactly when the Airish Borchardt property holds. Okay, so now what about all the subsets in between singletons and like everything except 0? So that might be an interesting problem. And the main reason I asked, I put this question here is that we do have such a characterization for cycles for finite groups. So this is a joint work with Kwan and and Hendry and Golin, that we can actually characterize what's, as long as a group is finite, we can characterize exactly the subgroups, subsets L, such that cycles of length in L satisfy the Airish Borchardt property. But I don't know what such characterization for A is. Okay, so yeah, I'll stop here. And thank you for your attention.
Thank you, Youngho. That was a great talk. Everyone, let's unmute and then we'll clap. I'll count to 3 and then we'll clap. So 1, 2, 3, clap. Okay. And does anyone have any questions?
I actually have quite a few questions. Let me start with one. Bruce Reed showed that the odd cycles don't have the Airish-Borchardt property, but then he showed that if you don't have the Airish-Borchardt property, if you give me a graph and the Airish-Borchardt property isn't working, then you have your favorite projective planar graph with even faces.
Yeah.
And so I imagine that for nearly every question you've mentioned where things go wrong, there would be a natural candidate of an obstruction.
Yeah. Yeah, I haven't really thought it through, but I would guess that the constructions that I showed you are exactly the structures that you would get. So, for example, if you take this example, the structure that we would get is some large wall where every cycle has length 0, except we have these many linkages on top of the wall that are in sort of in series, not in the echelon wall, but we have in series, and they all have the same. So I imagine that's you would get that sort of a structure as the instruction.
And I also imagine that you could push it a bit further and get I suspect with odd cycles, for example, you can show that a min-max theorem where you're not just having hitting sets where your objects are graphs embedded in surfaces with even faces, and so you could get a qualitative characterization where you push it a bit further and get a qualitative characterization. Do you think you might be able to get something like that for? You understand what I'm saying for odd cycles? So for odd cycles, I imagine that one reason why you wouldn't be able to find a lot of disjoint odd cycles is that your graph might be embedded in a surface of bounded genus, so that all of the odd cycles are one-sided. You can't have a lot of disjoint one-sided circuits, cycles. And you could probably turn that into a min-max characterization, I would guess.
What kind of a min-max?
Well, you would be deleting vertices, and then you'd be left with things that look like that.
Yeah. Okay, that's interesting.
And I'm wondering if something like that might also be true for your questions. The ones where you don't have the Airish-Borchardt property.
Yeah.
And my last question is a mixed version, moving to a mixed version of the undirected and directed, where you just have edges and you go in different directions and you pay a different cost from the monoidal group for going
I actually had a few more slides at the end, but I decided not to. We were out of time. But yeah, so we can ask about like directed cycles. So if you look at directed cycles, I mean, here we can sort of bidirect the edges. But if you just, I mean, more generally, we can just look at directed cycles where, I mean, I'm allowed to have both directions, but I'm only looking at cycles that are directed cycles in the underlying graph, and I just put arbitrary weights on these edges. So yeah, I didn't mention it, but there has been some recent results for directed cycles, Airish push-up property. So in particular, there's a recent result from 2020 that directed odd cycles satisfy the half-integral Airish push-up property. So it might be very interesting to see if we can sort of generalize these directed non-zero cycles in group label graphs. And there's also this directed flat wall theorem for directed cycles. So there's recently been quite a few results on structural results on directed graphs, and it might be possible to use some of these for the Airish push-up property. And this would really generalize both the directed model and the undirected model at the same time. But yeah, it's an interesting question. It seems difficult though.
Okay, those are my questions. Thanks.
Does anyone else want to ask a question? I just had one actually about, so for the results that you get the Airish push-up property, do we know what the function is in any cases? Or maybe that's a mean question.
Yeah, so anything that goes through these graph-Meyer tools will be very large. I haven't gone through and calculated the bounds.
Okay.
But actually, I mean, for the directed model, the bounds are very nice. Right? The non-zero A path, the function is 2, like multiplied by 2. And yeah, so the second result here, for gamma 0 A paths, the bound here is also not as bad. I think it's something like 12 times the maximum size of packing times the size of the group. So so here, when we look at 0 A paths, the bound necessarily has to grow with the size of the group because of this construction. So if the group is large enough, we can keep finding more elements that are where we can construct this counter example. So the bound does necessarily needs to grow with the size of the group. But other than that, for 0 A paths in directed group label graphs, it is linear. But for the undirected model, I don't know what the optimal bound is.
All right. Thank you, Youngho. That was great. I'm going to stop the recording there, and we can have some informal discussion.